Good evening everyone, welcome to one concept per day portal, and so far we had been doing lots of tests. So this is something like yesterday I had posted one test paper on interference and single slit diffraction on my WhatsApp portal. For those who are newly viewing this video, this is the paper that was been posted, and the link for my WhatsApp portal is as such: https rebrand is R here, rebrand.ly slash IB physics with raw. This is the link for this. You just type this one in the browser, you will automatically get an WhatsApp group, and then you can join that. And that's a admin assisted group, so you will not be able to send any messages to me, but I can always communicate. I will be every day by morning 8 a.m. Usually it is 8 a.m. Sometimes I send it one day before itself. Okay, yesterday for example I sent this across because today I had some work. Okay, so the next day, so next day evening by 8 p.m. this video will be posted across in my YouTube. I hope you know what is the YouTube channel of mine. YouTube channel is IB Physics with Raw. Okay, so you just type in IB Physics with Raw in Google, you observe that there are lots of pages which comes with the same name. So all pages of mine which is related to Facebook or Instagram or Twitter or maybe my website. The website also has the same address, which is ibphysicswithraw.com. Okay, you can go through this, and you will be able to see there are lots of past papers which has been put the solutions for it for paper 1, and this is what it is. Okay, now let us start solving this. So for today's problems, it is about interference and diffraction. So this is a problem which I have taken from 2005 May, and this is from the HL paper TZ1. Okay, so the old papers are really good enough in IB. So they give a lot of insights into the concepts, very depth insights. You can understand the concept also at the same time while you start solving these kinds of problems. Okay. So the problem reads as such: the diagram below shows is an arrangement for observing the interference pattern produced on the screen when the light from two narrow slits S1 and S2 overlaps. A beam of light from a laser is incident on the slits, and after passing through slits, the slit is incident on the screen. So you have a light from laser, it falls onto the two slits over here. This is one slit, this is the other slit. Okay, and then the separation between the slits is large compared to the width of the slits, and the distance between the slits and the screen is large compared to the slit separation. What does it tell you? It tells you separation between the slits. This distance is larger. This distance is larger as compared to the slit width over here, and this distance, which you call it as capital D, this capital D is also larger than the small d. That's what it is. Okay, so why do we need all these conditions? We need these conditions to understand that there is an interference pattern that is being produced. Okay, then explain why an interference pattern will not be produced on the screen if the laser is replaced by a tungsten filament light. What I'm going to do, I'm going to remove this laser from here, and I am going to put a tungsten over here. So what will happen when I replace this laser with a tungsten? Okay, so as a result of it, what will happen? So the waves that are being generated over here will be out of coherence, right? Because laser is something like, okay, all of them will be having a coherent source. Okay, that means the path difference between one wave and the other will always be equal to a constant. It doesn't change. But while when I use a tungsten lamp, it is not so. It can give you waves randomly. As a result of it, okay, you will not be getting the same path difference. Now, how does it affect? If you ask me this question, then let us see why does the interference happens. What happens is you have one wave, so the wavefront that you get over here, you get a wavefront like this, right? You get a wavefront like this. So I'll take one ray from here and see to it that it hits at this point. Okay, now there is one more ray which I will take from here. And then I'll see to it that this ray also travels in straight lines and it hits this one here. Now as a result of this, now what I do is I drop a perpendicular here. Now how do I drop a perpendicular? Okay, so what I do is I find this 90 degree, or maybe I take this as your compass point, use a compass over here, take a pencil point over here, draw an arc of a circle like this. Okay, draw an arc of a circle like this over here. So as a result of this, now this arc of a circle I am just considering to be a straight line. I'm giving some amount of theory over here. Just understand. Okay, if this is 90 degrees, and then what can happen is, so this wave, suppose, so these two, let me call this as S1, this is P over here, this is your S2, and this is your N over here, normal N over here. So therefore, now I can write, since I have drawn a circle, I can now write S1P is equal to NP. S1P equal to NP. That means, why do I write this? The reason is because, if let me assume that there is a wave which is going positive like this, negative like this, positive like this, negative like this, and so on. Okay. If I say there are 25 waves in this length, then how many waves will be there? Here also there will be 25 waves. Here also, if there are 25 waves, if there are. Okay, which means what? If this is positive going upside down, upside one here, and this is also positively going wave, then here this positive and this positive will add to give rise to a larger positive over here. And this negative and this negative will add to give rise to a larger negative over here. Let us say if this amplitude is A and this amplitude is A, this amplitude will become 2A over here. And this amplitude will become minus 2A over here. So what's happening? Two amplitudes are joining together to give rise to a bright wave. Okay, this is what you can get over here. Now, if you want to get this one over here, now how should this be? You know, waves are continuous, they are never discontinuous. So therefore, here this should be also be like this over here. See, this ending point and the starting point should join together. It should be a continuity. That's what it should be. So if you have one wave in this gap, in this S2n, what is the length of this wave? This length of this wave is lambda, right? One wavelength. Now I can also call this S2n as the path difference. Your path difference. What is the path difference value equal to? Lambda. Now you can always argue with me saying that why should it be S2n equal to 1 lambda? Can't it be 2 lambda? Definitely it can be 2 lambda. Now one more person says, can it be 3 lambda? It can be 3 lambda, 4 lambda, 5 lambda. Okay, as long as the difference here is always equal to n times lambda, when n is an integer, you will always get a bright point over here. You will always get a bright band over there or bright fringe over there. Okay, as a result of it, so when you get n is equal to an integer, n is equal to an integer, then definitely you will get this as a bright fringe. Now, the other thing that can happen is that, okay, if suppose if this is a negative going pulse and this is a positive going pulse, then what can happen? This negative will add up with this positive. As a result of this, you will get a 0 over here. So if this has to go negative, I will take up a different pen color to show destructive difference, destructive interference. Okay, this one is called as constructive interference. And suppose, okay, if this is positively going wave, this is positively going wave like this, and this is now going into negatively going wave like this over here. If the wave that comes here is negative and this is positive, then what can happen? This negative and this positive will join together to give rise to 0. Okay, so now as a result of it, you will get a 0 here. And if this has to be 0, now what will this case be? Okay, if this has to be negative and this is positive, then might be, because of continuity, I can now say this has to be a wave like this. Either it has to be a 1/2 wavelength here, or it has to be a wave like this over here. It has to be a wave like this over here, which means this is one full wavelength and one more half wavelength. It means it should be 3/2 times wavelength, 3/2 wavelengths or 1.5 wavelengths, right? If this is the case, definitely you will get 0 over here. So either you should get positive or it should be negative, and this should be continuously the same type of thing should happen. Okay, but this is seen in case of a laser. Okay, both of them can either give to positive, can either give to negative, anything can happen over here. But in case of a tungsten lamp, when the waves itself here is not coming in phase, then what can happen? Sometimes positive, sometimes negative, and so on. The pattern that you get here will not be sustainable. Okay, so now let us write down here what is that we need to write. Explain why an interference pattern will not be observed on the screen if the laser is replaced with a tungsten filament lamp. The first one is, when the laser is replaced with a filament lamp, what will happen? The phase difference will not be a constant. The phase difference will not be a constant. This is the first one. And second one, they are non-coherent. Non-coherent. Okay, first is what we'll do is we'll write this as path difference. Path difference and hence, okay, right, and hence they are non-coherent. As a result of it, what can happen? Sustained interference pattern is not observed. This is what can happen. Okay, sometimes you get a bright fringe, sometimes you get a dark fringe, and it can keep on varying over. Okay, now let us move on to the next question. On the axis below, draw a sketch graph to show how the intensity of the observed interference pattern varies with the distance along the screen. Okay, so what is this now? This is a YDSC, Young's double slit experiment with a laser. Now, what kind of graph do you get over here? You should get a proper maxima and a proper minima which are equi-spaced, right? So therefore, what I will do is I will consider one wave like this, then another wave over here like this over here, like this over here. Now this x represents the maxima at the center of the screen, and then you will get like this, then like this, and once again like this, once again like this. I have written 2 here. Similarly, I will write here also. I will write here also. I will write here also like this. Okay. Now what is important? This is for 2 marks. How do you write? The first one is central maxima. Central maxima should be at x. Okay. 1 mark for central maxima, and the other mark for the distances here. See, this point and this point and this point and this point, all this are seen to be equidistant over here. Okay, equidistant maxima is observed. Okay, so in case of an YDSC experiment, what is YDSC? Young's double slit experiment. You observe, okay, equidistant maxima has been observed and central maxima is also seen, and all of them are having the same brightness. You may be comparing this one with a single slit experiment. In a single slit experiment, what will be happening? You would have seen the graphs to be written like this. You will have something like this, and then this will diminish like this, and you come out like this. It will be like this. See, note the differences between these two. Okay, in an interference pattern, you get a pattern like this. In a diffraction pattern, you get a pattern like this. What is here? This is your intensity, same units. This is your intensity, and this is your position. Maybe you can say it's a positional coordinate. You can say like that also. Okay, now let us move on to the next. The wavelength of light from laser is 633 nanometers, and the angular separation of the bright fringes on the screen is 400 to the power minus 4 radians. Calculate the distance between S1 and S2. Okay, first thing is that let us write down the fringe width. Fringe width is given by lambda capital D divided by small d. Okay, now what do you mean by what is given here? Lambda is given to you. Lambda is given to you. Angular separation. What do you mean by angular separation? Angular separation is nothing but the ratio of beta divided by capital D. Fringe width, so distance between the slit and the screen. Okay, D. So now this should now be equal to lambda divided by D. Now what is being given? This value you term it as theta, and this value is given to you, which is equal to 4 into 10 power minus 4. And calculate the distance between S1 and S2. What is that you need to find? Value of D. So now it's easier. So what you will do is you'll write D is equal to lambda divided by theta. Lambda is 633 into 10 to the power of minus 9 divided by theta. What is theta? 4 into 10 to the power of minus 4. We are not going to change anything because theta is already in radians. Okay, just going to put like this. And now let us calculate this value. Let me take up my calculator. So it is 633 divided by 4. I just take the numbers, which is 158.25. 158.25 multiplied by 10 to the power of minus 9 plus 4 should be minus 5. Okay, now what I will do is, what is this unit? This is in meters over here. I'll write it in millimeters. So this should be 10 power, I'll take 0.15 millimeter. This is the answer over here. 10 power minus 5 minus 4 minus 3, I'm sorry, not 0.15. This is 1. Take it here. 1.58 millimeter. This will be the distance between the two slits S1 and S2. Okay, now let us move on to the next one. Consider now a thought experiment in which the light from the laser is replaced by a beam of electrons. What did you do? You replace this laser with a beam of electrons. that has been accelerated from rest. From rest means initial velocity is equal to 0 through a potential difference v. So potential difference is given. So now what are we combining this? We are combining optics with modern physics. That is the de Broglie wavelength and all this. That's what it says. Deduce that the de Broglie wavelength lambda for the electrons is given by lambda equal to h by 2 me capital V small e. Okay, h is Planck's constant, m is mass, v is the electron charge. Now you know what is de Broglie wavelength. What is de Broglie wavelength? By de Broglie wavelength is given by lambda equal to h by p, where h is the Planck's constant, p is the momentum. Now next is, if I have h over here, momentum, as you know, you can write this as m into v. Now from all these values what is given, how do I get the velocity here? That's the question. Okay, whenever you need to get the value of velocity, if you are not able to use your equations of motion, remember you can always go with energy methods. Okay, there are only two methods to connect velocity to any of the variables. One is equations of motion, the other one is energy method. What is energy method? Kinetic energy plus potential energy equal to total energy. That's what you need to do. Okay, now let us start. See, I will not be able to use your equations of motion, nothing I know about it. Okay, so as a result of it, now let us start with the energy methods. Now what do we have here? You have an electron, this is your electron, and you say you are accelerating it through a potential difference v. How do you accelerate an electron? When an electron is at rest, how do you kick this electron? So it starts moving with the velocity v. What is that you do? You apply an electric field. Okay, let us apply an electric field. How do you apply an electric field? Let us say I have drawn an arrow like this, which means I expect the electron to move like this over here. So I will put an electric field here. I will not put it here, because if I put the plates over here, I can expect the electron to go downward like this, which is not possible, or maybe upward like this. I'm not doing this because velocity vector is like this. We know that the direction of velocity vector and direction of the displacement vector both are in the same direction. So therefore, remember this, direction of velocity vector is equal to direction of velocity, this displacement vector. Remember, this s is not equal to v. Okay, once again I'm telling you, s is not equal to v here. It only tells me the directions of s and directions of v are same. Okay, I'm sorry, I think I should have not equated this. Okay, directions of s and v, I will write it like this. Directions of s and v are same. Okay, always, any kind of problem you take. Right, now if I consider here an electron, you should make an electron to move like this. How do you make this electron to move like this? See, you can push this electron from here. How do you push this electron? So put this part as negative and put this part as positive, right? So what will happen? The negative charges on this plate will now try to push it like this. Positive charges will attract it. So it's a double bonus for it. Definitely electron will start moving like this. Okay, now we have got this. Now when I say negative and positive, how do you achieve this? You put a battery here, such that negative terminal is connected here, positive terminal is connected here, and then you see there's a potential difference between these two. What is the potential difference? It's equal to the potential difference of the battery. Okay, now we have put V here. Now what is the energy acquired by an electron when it is subjected to a potential difference? The energy acquired is nothing but work done. What is work done? Work done is nothing but Q multiplied by V, right? Charge multiplied by potential difference. We already learned this. So Q multiplied by V. What is Q here? Electron. We'll just take E, and V I'll just put value of V here. Okay. Now you can put minus E also. I'll take only the energy magnitude of this, E into V over here. Okay. Now we have got energy. Now what should this energy be? See, the electron is receiving this energy, and as a result of it, the electron is now started to move from rest and going to in this direction. So what is that energy called as? Not potential energy, it is kinetic energy. So I can equate this one to be equal to half mv square. Now when I equate it, now you see somewhere these are very similar to it, right? So let us do this. So half mv square is equal to E into V, and I can now write V square is equal to 2EV divided by m, right? Or in other words, I can now write, this implies V is equal to square root of 2EV divided by m. So what until here? What's the next step? The next step is I want lambda. What is the value of lambda? I'll write lambda here. Lambda is equal to h by p. Okay, which should be h divided by m into, substitute this value of v. square root of 2EV divided by M, which should be h divided by, see, this is M and root M here. What will happen? This can be written as a, okay, root M into root of 2EV, which can be written as h divided by square root of 2ME capital V. Now let us see whether we have got the same answer. H divided by root of 2ME V into E. What is that I have written? I have written as E into V. Okay, both are same. So therefore, the lambda value is given by this equation. Okay, I hope you understood this. If not, do let me know. I have to make one more slow video. Right, this is not very fast. It's slow only, but anyway, you can practice it once again. Right, next. The electron beam is accelerated from rest once again. Okay, whenever you have terms like this, immediately write down the values from rest to a potential difference 400 volts. Calculate the separation of S1 and S2 such that the angular separation of the electron interference fringes theta is given here. What is being asking? Again, he is asking you to find out the value of D. So we have already found out this value of D, right? Where did we find? We found out the value of D here. What did we find? We found out 1.58 millimeter. When the value of lambda was something like 633 into 10 power minus 9. Okay. Now the value of lambda changes. What is the value of new value of lambda? New value of lambda we are going to calculate. We are not yet found out, but we already got a formula here. Okay. So therefore we are going to use the same formula. What is the formula here? The formula which we use is D equal to lambda by theta. Let me write it down. I have D is equal to lambda by theta. I know what's the value of theta, but I do not know what's the value of lambda. Let us substitute this also. So towards it, first let me calculate the value of lambda. So how do I calculate the value of lambda? I will do it here. I calculate the value of lambda. Lambda formula I will take from here. You know, in IP, always the previous problem's output will be the input for the next problem. Okay, so you get a clue from there. Okay, so you need not think, how do I do it? So if you go blank in the exam, then you definitely have this clue over here. Remember this clue? In physics, I have seen so many papers, it works only in this principle. So I'll substitute this value h divided by square root of 2ME into capital, which should now be equal to, right here, so conserve the space, 6.63 into 10 to the power of minus 34 divided by, if you take the data booklet, you will be able to find 2 multiplied by, this is 9.1 into 10 to the power of minus 31 multiplied by value of V, 1.6 into 10 to the power of minus 19, right, multiplied by, I put a bracket here, V. What's the value of V? 400 value volts. 400 volts, right? 400 volts. Let me check it out once again. 400 volts. It's given. Okay. Now I'll substitute all these values and get the answer. So therefore, value of lambda is equal to, my calculator. So I have, I'll once again write this as 6.63 into 10 to the power of minus 34 divided by square root of, let us write down this value here, 2 into 9.1 multiplied by 1.6 multiplied by 400. I get this as 11,648. 11,648 into, I left the powers over here. This 31, this is 19, this will be 10 to the power of minus 50. Let me simplify this further. What do we get here? 11,648, I'll take the square root of this. You get 107. I take the reciprocal of this. I get 0.0093. Then I multiplied this by 6.63. When I do this, I get 0.0614. 0.0614 multiplied by, here I have 10 power minus 50. I'll write 10 power minus 34 as such, divided by, see, I took only the square root of this one. I didn't take this one. So this will be 10 power minus 50 divided by 2 will be minus 25. Now, finally, I can now write this as 0.0614 multiplied by 10 to the power of minus 34. This becomes plus 25. So this will be minus 9. Okay, what is the lambda? Lambda is in meters. Okay, or in other words, I can now write this as 6.1 into 10 to the power of, see how much I have moved, shifted this dot to this point to 1, 2 digits. So I can write this as 10 to the power of minus 11 meters. So I have got the value of lambda here. What's the next step? I'm going to substitute here. So d is equal to 6.1 into 10 to the power of minus lambda divided by 4 into 10 to the power of minus 4. When I do this, what do I get? Let me redo it once again. So this will be around 6.1 divided by 4 is equal to 1.52, 1.53 nearly. 1.53 into 10 to the power of minus 11 plus 4 will be equal to minus 7 meters over here. Okay, so this is what I get. What is this now? The separation of S1 and S2. Okay, when you use this one, right? Then so with this we come to an end to the first problem. In the next video we will see the second problem. Thank you.